Okay, so let's bring everything together what we have covered so far, and let's review again a little bit some of the concepts. So let's say you produce something and you found this is your production function. So that's the same that we used earlier. And you produce a good X, and this is your utility from consuming X. So the question now is, how many X will you produce? And what you have learned from an earlier video is that as long as the marginal utility of X is greater than the marginal cost of producing X, you feel you get more utility than cost, so you keep on consuming. And the optimum is, so as long as MUX, the marginal utility of X, is greater than the marginal cost, you keep on producing. You keep on producing. And we said the utility function looks something like this. That's the utility from consuming X. But the marginal utility looks different. So the marginal utility of X looks something like this, because the slope gets flatter and flatter here. Okay, for the marginal cost function, we said a typical cost function is inversely S-shaped, or something like this, and the marginal cost function looks something like this. Okay, so now, as long as the marginal utility, let's just take those two, let's just take a look at those two graphs and put them into one graph. Okay. So we have here X, and we said, okay, the marginal utility of X is maybe something like this. That's the marginal utility of X. And maybe the marginal cost, let's give it a different color, maybe, I don't know, green, looks maybe something like this. Maybe I draw it more drastically, so. Okay. And then it goes maybe up again. So now, as long as the marginal utility, the blue one, is greater than the marginal cost, you start consuming more and more and producing more and more. But where the marginal utility equals to the marginal cost, that is where you have the optimum. So whenever the marginal utility of X is equal to the marginal cost, which is this point, you have reached a maximum. Because you will say, well, if my willingness to pay for something is exactly the same as what it costs to produce, well, that's where you should stop. You will not produce something which causes you more extra cost than what it gives you extra utility. So in other words, we need to find the point where marginal utility equals to marginal cost. Okay, so let me just delete all that ink again. So we know that your optimum utility, which we call U star, is where the marginal utility of X equals the marginal cost. So let's find that point. So the marginal utility, we derived that earlier, we derive that as 8 over the square root of x. And the marginal cost was 0.15 x squared minus 1.5 x plus 4. Okay, so now we just have to find the point where 8 over the square root of x is equal to 0.15 x squared minus 1.5 x plus 4. Well, that's a pretty complicated function, and it will take me quite a while to figure that out. The good thing is, we can use Excel for that. And so, and I'll show you how that works. That's very useful. So I want to solve the x where both are the same. So I can rearrange this equation, and I can say I basically subtract on both sides 8 over the square root of x. And then I get 0.5 x squared minus 1.5 x plus 4 minus, because I subtract that, 8 over the square root of x. That needs to be equal to 0. So at what x is this equal to 0? I couldn't figure that out quickly, but this is where Excel comes into play. And let's just let me show you something how we can solve that in Excel. And in fact, I will show you 2 ways of doing it. Okay, let's pull up Excel. And then there is something which is called goal seek. So you can search for goal seek, and you see that pulls up a little box, goal seek. So you search for it. It is probably somewhere under data, what if analysis. There you can find it too. Actually, let me quickly show it. I think it's data, what if analysis, goal seek. So you can also. Okay, so, but the first thing that we need to do is we have, let's say, our output cell that we want to have equal to 0. And then we have an input, and the input is our x. So let's say our x is equal to 1. I'll just enter here quickly 1. And our formula okay, so I have this equation here. Let me actually quickly see if I can snip that out. Yeah. Okay. So I snipped that out, and let's say put it here again. Okay, I want to find the x that solves this equation and make it equal to 0. So let's just assume the input x is currently it is 1. Then I would say here I use this formula equals to 0.15 times x minus 1.5 times, actually x squared, minus 1.5 times x plus 4 minus 8 divided by the square root of this x. Okay, so now this is negative 5.35 if x is 1. Okay, so maybe we can double check that. 0.15 times 1 minus 1.5 plus 4 minus 8 over 1. Yeah, that's probably negative 5.35. So again, 0.15 times the x squared minus 1.5 x plus 4 minus 8. Okay, so this formula is correct. So now I can play around, I can say, what do I get if I enter 2? Maybe then next I try 3. Okay, it's slowly getting less. And I need to get it to 0 by changing, the cell E4. Okay, 6, okay, I'm getting close to 7, maybe 8. Okay, maybe 9. Ooh, okay, maybe 10. Oh, okay, it must be between 9 and 10. But of course, I don't want to play around with the cell E4 and check all values until I get 0. Because this is essentially what goal-seek does. So if we go back to goal-seek, or if you want to go to data, what-if analysis, goal-seek, so you say, I want to set the cell, not E4, but this one, the cell E5, the output, to the value 0 by changing this cell that I just changed all the time. But instead of me entering all those different values, I let Excel do it. Okay, so I just press OK. And now it just plays around. And we get the value 9.01. Okay, so that's good enough for our purposes. And this value, negative 1.6, this is essentially 0. Okay, so the best value we can get is 9. So 9 is, so let's just forget about all those decimals. So 9 is our optimum value. Okay, so the next thing we want to see is if that is actually true. So we can also visualize it. So let's take a look at the function, the marginal cost function and the marginal utility function. And so first I create again a column from 0 to, let's say, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have to take a look at the marginal utility. And we said the marginal utility was 8 divided by the square root of x. And now we get again an error message, but it's not a big deal. Okay, and the marginal cost was equal to 0.15 times x squared minus 1.5 times x plus 4. That was the marginal cost function. Okay, so now let's see, you see at 9 they're pretty much the same. There's no big difference, so this is the best value we can get. So if we just limit everything to okay, if I just limit format cells number 1 decimal. Okay, you see that in 9, at the quantity of 9, you maximize your utility because the marginal utility is exactly equal to the marginal cost. But before you reach the value of 9, let's say 1, if you consume 1, you get an extra utility of 8, but you have to pay only 2.7 for it. Then you have a second one. You get another utility of 5.7 extra, but you have to pay only 1.6. So you get net utility Then you think, shall I have a third one? You get another utility of 4.6, but you have to pay only 0.9. And then you have a fourth one, you get an extra utility of 4, you have to pay only 0.4. But then after a while, the costs go up again. For example, if you have an eighth cookie, which is X, let's say, you get an extra utility of 2.8, but it costs you only 1.6. But at 9, you get exactly 2.7 utility, but it also costs you 2.7, so you're technically indifferent. But we would argue that whenever, marginal utility equals marginal cost, this indifference breaks in favor of consuming. But you definitely will not have a 10th cookie, because you only feel like it gives me a utility of 2.5, so your willingness to pay is only 2.5, and there is no way you pay another 4 to get that cookie, because the extra cost is greater than the extra utility. So now let's see what we get when we visualize that. So insert recommended chart. So this is what it is, and you see the blue line is the marginal utility, the orange line is the marginal cost, and here at the quantity of 9 we get marginal utility equals marginal cost, and our total utility is, when we consume 1, we get this distance in utility, and then we have a second, we get this one in utility, and then this and this and this. This distance, or this difference, is what we accumulate in total utility. Okay, so how much total utility do we get? So we know our optimum is 9. That's the optimum consumption level. Okay, so if we plug in here 9, so then, okay, maybe I'll just add that quickly, the total cost and the total utility. So the total cost we said is equal to 0.05 times 9 cubed minus 0.75 times 9 squared. Okay, what was the other one? Plus 4x plus 5 plus 4 times 9 plus 4. So the total cost is 15.7. Oh, it's actually plus 5. So the total cost is 16.7. And what is the total utility? The total utility, that was equal to 16 times the square root of 9. So that's 348. So the net utility that you get, is the difference between the total utility and the total cost. So you get a total of 31.3 in total utility. And that is the profit maximizing utility that you can get at the quantity of 9. Okay, so that's it. I hope you don't have to, at this point, you don't have to know everything and replicate, but you should have a feeling for it. So you should see that in a graph, when, let's say, the marginal utility hits the marginal cost, that this is a maximum utility by this point you've accumulated a maximum utility. But we will review that in more detail in the problem set. Okay, so I hope you found that useful. So see you in the next video.